Okay, so since we will have the midterm um, on this Thursday, so I decided to give you some problems and show you how to solve problems. Um, so feel free to stop me if you have any question or get confused. You can just unmute yourself and speak out. We can discuss. So I prepared like 5 problems about like what we learned before, like the divergence theorem and Green's theorem and also Stokes theorem, and also how to do surface integral and volume integral. So because we have only 15 minutes, for each problem, I will give you like about 1 minute to read the problems and think about if this is an exam problem, how will you approach this problem? Then we can walk through together. And yeah, you may take a look at this first one, and then we can go through together. Okay, so basically for this kind of problems, the first step you need to do is to figure out what's the integration region, right? So basically first you need to figure out the, sorry. So for this one, from the problem, you can see that it's from point A, it's not to 0, to point D, 0, 1, and to point B, minus not to 0. So basically we need to do a line integral cosine y dx minus exponential x sine y dx, sorry, dy. So the second step is to determine which theorem we need to use. So so in this case, we can apply the Green's theorem or Stokes theorem, whatever. Because here's a 2-dimensional version, so we can just say it's Green's theorem. And when we apply the Green's theorem, we will always need to be careful about the condition. So here the loop, the integral is not closed. We want to form a closed loop, right? Otherwise, it's not correct. So basically, let's denote the original loop, original path as path 1. So then it's just path 1 cosine dx minus x sine y dy equal to, we want to construct a closed loop, right? So to form a closed loop, let's choose another path from A directly to point B. Let's call this path 2. So to form a closed loop, so path 1 minus path 2 will give us closed loop, because minus path 2 corresponding to the from B to A, right? Minus sign corresponding to reverse the direction. So A to B and B to A, then form a closed loop. So this is cosine y dx minus exponential x sine y dy. But this guy, so this guy is not equal to this guy. So to make them equal, we add another path 2. right? So you can say this plus 2 canceled with this plus 2, left with the plus 1. So this is what was the trick we do when we have some unclosed loop or surface. So combined with, so this 1 minus 2, we get a closed loop. Yeah, from A to D to B to A. Basically, it's this triangle. Any question about this step? Okay, so I guess it's clear. Just let me know if you have any question. So basically, once we have a closed loop, we know that we can apply the theorem. I mean, okay, so it's like you know, become a what's the name? Next area integral dx dy. The integration region is the region within the loop, right? That's denoted as omega. And the integrand is given by the Green's theorem. Is like a partial x. This guy. So it's minus ex sine.
I have a quick question. Is the right-hand side the integral 1 minus integral 2 plus integral 2, or is that because you're subtracting integral 2? Like, is that whole right side together?
Right. So okay. So so the left-hand side is just integral 1, and the right-hand side is integral 1 minus integral 2 plus integral 2. So basically, they are equal. You can say directly this guy, the second term cancel with the third term. But we want to combine the first term with the second term to make it a closed loop, and then apply the theorem.
So you'll only actually do this if you don't already have a closed loop, right?
Sorry, what's that?
The only reason you're doing this is because we don't have a closed loop, right?
Right, exactly, yeah.
Oh, so are you applying a Green's theorem to that first set and then adding on integral 2?
Right.
Okay.
Right.
Thank you.
Yeah, that's what we usually do, right? So whenever you have something unclosed, we add something to make it closed, but to make them equal, we need to subtract the same thing, right? So with here we kind of a minus 2 to make the loop close, and we add 2 to make them equal. So basically, we have, let me add another page. So basically, what we have on the right-hand side is a closed loop, like the triangle I drew before. X cosine y dx minus ax sine, sine y dy. And also another piece, which is this one. As we will see later, for the for the divergence theorem, we have similar stuff. In that case, instead of add a loop, add a line integral, we add a like surface integral to make the surface closed. So basically, for the first step, for the first this kind of a closed loop integral, we apply the Green's theorem. I think everyone can do this. Just plug into the formula, and you will find that this guy goes to 0, and only left with the second term. So here I just ignore the calculation. I will upload the solution after this discussion. So you can take a look at the details. Here I just want to sketch how to approach this kind of problems, just in case, whatever. What's that?
Oh, thank you.
Okay, sure. Right. So for this integral is easier because the path 2, we know that you can say on the path 2, the y is 1 with 0. The x goes from log 2 to minus log 2, right? So basically, this is the path 2. Let's copy that. Paste. So you can say y equal to 0. Correspond. So y equal to 0. Of course, dy is 0, right? There's no change in the y direction. So meaning that this guy just goes to 0. And the y equal to 0, cosine 0 is 1. So this guy is 1. So basically, it's an integral of x. And x goes from log 2 to minus log 2. And you can do this integral by yourself. This is exponential x, so it's exponential x minus log 2 equal to exponential minus log 2 minus exponential log 2. So this is e log 1/2 minus log 2. The property of this kind of a log and exponential give us this, which is minus 3/2. So any question?
Yeah, could you just reiterate, please, why the double integral from Green's theorem was 0?
Oh, okay. So you know the Green theorem is like for this kind of closed loop, it's given by oops, it's given by partial x, this guy, which is minus exponential x sine y, and minus partial y, this guy, right? If I remember correctly. Cosine y. And this integral is integrate over the region within the triangle, within the loop. So you can say this integrand is 0, right? So you take a partial x. The first term give us minus ex sine y minus this term. So cosine y, take a derivative, get a minus sine y. This is 0.
Okay, that makes sense. Thank you.
Right, yeah. I mean, so the purpose of giving this problem is kind of show you what's the general approach for this kind of problems, like this kind. So usually you have a problem that you can apply the Gauss, like the divergence theorem. In this case, here's the Stokes theorem or Green's theorem, whatever you want to call. First, you need to figure out what's the integration region. You can draw this kind of pictures. Sometimes you find the integration region is not closed. In that case, you cannot apply the theorem directly. You need to do this kind of trick to make the integration region closed. And at the same time, there's another piece corresponding to to make this kind of equation equal. So in general, there are two pieces. One is a closed loop integral. For the divergence theorem is a closed surface integral. And there's another piece which is a standard line integral or a standard surface integral. Usually it's easier to do compared with original line integral or original surface integral. So for the first piece, for the closed one, you can apply the theorem you want. And for the for the another piece, you can do this kind of calculation directly very easily. Yeah. Okay, so the exercise 2 is also about the line integral, but in a 3-dimensional space. Let's skip this one. I just want to show you more examples. This one, is similar to the exercise 1. So let's skip it and let's look at, if we have time, we'll go back to, we can come back to this exercise 2. Let's look at exercise 3. Yeah. So you can take a look and say how will you approach this problem.
You could use the Stokes theorem in 3D because it would be easier to calculate the volume integral.
You mean the divergence theorem?
The divergence theorem in 3D.
Right. Yeah, but the here's the similar problem is the surface is not closed. Right, let's take a look at this problem. Right, the general idea is correct. Basically, we need to draw the integration region first. So basically, it's given by this constraint. So first, it's a cylinder. Okay, so let's draw like this. And the cylinder between 0 and 3. This is 3. So basically, the integration region is owning this kind of surface. So it's not closed because there's a like a bottom disk and also a top disk. It's not included in this integral.
How do you know that? Like it's not included?
So okay, so because this is because the integral region is given by this constraint, right?
Oh, because x squared plus y squared equals 1 instead of
exactly right, exactly right. So for any point on the disk, x squared plus y squared is smaller than 1. So it's not on this.
Oh, right.
So it's kind of tricky. You need to be careful when you determine the integration region.
Can you repeat that a little bit more? That signal kept cutting out.
What's that? Can you repeat your question?
What did you say about x squared plus y squared being less than 1 again?
Oh, okay. So here I just want to argue that the integration region is the integration region does not include the top disk and the bottom disk, because any point on the disk, for example, assume it's x squared, assuming the point is x, y, and z, then x squared plus y squared is smaller than 1. Basically, the distance from this point to the z-axis is smaller than 1. But here, this constraint gives us the x squared plus y squared equal to 1, right? Meaning that the integration region does not include the top and the bottom disk. Right, okay, so let's, yeah, right. So the first step is to draw this kind of integration region to make sure you can see whether this is closed or not. And the second step is to determine which theorem you want to use. So for this kind of integral, we definitely want to use the divergence theorem to convert this kind of surface integral to a volume integral. Right. Let's see. But first, similar to what we did in our first problem, we want to make it a closed surface. So to make it a closed surface, let's call this cylinder surface 1. the normal vector, when you choose a surface, you always need to specify the normal direction of that surface. Here's the problem tells you is pointing outwards, and let's call this upper disk as surface 2. Let's use the red color. And assume the normal vector is pointing upwards. And also the bottom disk, surface 3, and pointing downwards, the normal direction. So it's minus z hat. Okay, so once we have this, we can start to do the calculation. Right. So originally we have 1, and then it's r dot sigma. Now we want to make a closed surface, so it's 1 plus 2 plus 3. But to make them equal, we need to minus 2 and minus 3. Does it make sense?
Yes, I had a quick question on whether or not we need to show work on integrating the volume integral. Like if we know that it's just going to be the volume of said cylinder, said sphere.
I see. I don't think you need that. That's too easy, right? It's just like the area times the height,
Right.
right? Yeah. You can write down directly, right? I'm pretty
Cool.
sure. Yeah.
Thank you.
Sure. Okay, so so the first term becomes a closed surface integral of this kind of a cylinder, including those 2 disks. And also, this is the reason why I choose the normal vector of the third surface, this disk, as the direction pointing downwards. Because when you want to make a closed surface integral, you always want this normal vector of the surface pointing outwards, right? So for this kind of a bottom disk, the pointing outwards meaning that it's pointing downwards. So it's minus z direction. Okay, so here the second surface, so it's r dot, the normal direction of this disk is z direction. So it becomes dx dy. And also the z equal to 3 on this disk. Similarly, for the third surface, the bottom disk, the direction is minus z hat, dx dy. But at the same time, we know that z equals 0. Any question? Okay, so just let me know if you have question. You can speak out. Okay, so this one, we can safely apply the divergence theorem, which is, becomes a volume integral. Oops. Minus this guy becomes r dot z hat. R is x, y, z. Dot z hat is 0, 0, 1. So equal to z, right? So it becomes z dx dy, and z equal to 3. So minus, so this minus sign cancel with this minus sign becomes plus sign, z equal to 0, and z dx dy. Right. So here, from this step to this step, for the first term, I apply the divergence theorem. For the second term, I just work out this r dot z hat. And the third term is also r dot z hat. There's no trick. So
I
this,
just want,
sorry?
sorry, I just want to ask, is that only applicable if it's a closed surface?
You mean for the divergence theorem?
Right, yeah, I'm getting mixed up which theorems require it to be a closed surface.
I see, right. So for the divergence theorem, we need a closed surface because we want to convert this surface integral to a volume integral, right? So for the volume integral, it's kind of a inside some closed surface. So we want the surface to be.
Oh, right.
So for the divergence theorem, for the Stokes theorem or the Green's theorem, you can say we are converting the line integral to a surface integral. In that case, the surface don't have to be closed, right? We only need the loop integral, the line integral to be closed because.
Oh, so you only need a closed loop for
right,
that case.
right. Okay.
Thank you.
Sure. Yeah, this is kind of a very good questions, and yeah, it's good to ask. You should be crystal clear about this kind of stuff. Otherwise, if the problem is complicated, then you may get confused. Right. Okay.
Can you talk about the direction of the normal vector again?
Okay. So yeah, that's actually a very important thing. That's why I say some words here. So basically, when you apply a divergence theorem, right? So you know that divergence theorem looks like whatever. So the volume, the boundary of volume, V. So let's use another vector, E ds plus, sorry, this guy equal to divergence of this guy. So here you have a ds. So the direction of this ds is the normal direction of that closed surface. And we choose that direction as the normal direction, like going outwards, like that direction as the normal direction. That is why I choose the normal direction of the bottom one as pointing downwards instead of pointing upwards, because I want this when this 1 plus 2 plus 3 form a closed loop, form a closed surface, I want at each point the normal direction pointing outwards for this kind of closed surface. That is the reason why I choose the normal direction as minus z hat. And for the bottom one, I choose the z hat.
I had a quick question.
Sure, yeah.
So if, let's say if you weren't using divergence theorem, you would have to calculate explicitly what n hat is to solve the integral, right?
M hat?
No, n hat, the normal vector. You would have to explicitly solve for.
Right, yeah.
So how would you go about doing that in the case that we wouldn't be able to apply divergence? Like, can you solve the normal vector?
Okay, so we have actually that's the so for this, you can say for this problem, the normal vector is easy to save. It's just because it's a disk, it's kind of a plate. So it's just pointing in the z direction minus z direction. In general, you're right. Maybe it's not a constant unit vector. But in that case, the divergence theorem has no advantages compared with calculating it directly, I think.
Yeah, that's what I mean. So if you had to calculate it directly, do you mind like actually solving for the?
Oh, you mean for this one?
Yeah. Huh.
Yeah. You can do it. I mean, I think this one is also. It's just I think it's just x y squared x squared plus y squared y squared plus y squared. For this one, I think n is given by this.
Okay.
Yeah, it's pointing in the radiant direction, right? It's like in the polar coordinate is kind of a r hat, right? So the third component is 0, and this one is this vector in the 2 dimension is just the r hat.
Okay, thank you.
Yeah, sure. Okay, right. So next, yeah. Any more questions? Yeah, it's good to ask questions. Well,
That's super helpful. So I see like the point of using the theorems is more so if you can make it closed by manipulating the integral, then you want to do that since in this case, the volume integral is really easy to calculate
right,
for the
exactly.
closed surface.
Right. That's the point. Yeah. Also, thanks for asking questions.
And just like in the same realm, there's a question on the homework about a curved surface of a hemisphere. So in that case, like you would want to close the hemisphere
Right. Exactly. Right.
by doing you could do the volume integral of a hemisphere, and then you could just subtract off the regular r dot z of the circle on the bottom.
Right. Exactly. That is quite similar to what we have here. The only difference is in that case we have only one disk. Here we have 2 disks.
Yeah, right. Okay, thank you. Yeah, that's super helpful.
Right. Cool.
Actually, I have a question from the homework. One of the homework question was like finding divergence of the curve of the A, and you showed that becomes 0. And I just wonder why divergence of the curve of A becomes 0 in general.
Divergence of curl is 0. Yeah, I mean, you can prove this in general, right?
Why that's the case?
You mean physically or what?
I mean, physically or mathematically, both are fine.
Mathematically is easy, and whenever you ask it why this is true, physically is quite difficult. For example, why there's a night is difficult to answer, right? So, mathematically you can prove it. You can prove it very easily. So you can say, sorry, the divergence. You can wait. Let's see. You can write this guy. In terms of IJK, so partial x, partial y, partial b. Okay, let's. I'm not sure whether you are familiar with Einstein, like the index notation. That's would be much easier, but.
I can say why mathematically is 0, but can you kind of give me one example that we can use in physical world?
Well, so let's see.
Well, the way that I'm kind of seeing it is that the curl is like, how much field, it kind of spins around. So if you're looking at the divergence, which is how much it diverges from a point, you can't, if you're looking at the spinning and you're looking at the diverging at the same time, so you're not going to have both, so they're 0. That's kind of how I see it.
Yeah, this is kind of a hand-waving way to understand it, right? Yeah. There's actually you can prove it with some pictures. Imagine something. You have a field, something like this, and yeah, but this yeah, it's kind of too far away from what I'm seeing here. Yeah, but this is an important equation.
Excuse me, can you later talk a little bit about the homework 3, problem 3?
Which one?
It's
okay. Let me
integral.
Let me take a look at the, because I haven't taken a look at the homework yet. Let's see.
Yeah, I only have a question about the integral range, like how to get the integral range from the revolution.
Okay, maybe you can stay after this discussion for like 10 more minutes. We can discuss.
Okay, thank you.
Right. Yeah. Okay, so basically, let's back to our problem here. Yeah, it's nice to asking so many questions, and yeah, the best way to learn something is by asking questions, right? Okay, so this guy is 3, right? Because R is X, Y, Z. When you take a divergence, you get 3. So constant. And the constant, this guy is nothing but the volume of the cylinder. So this guy minus Z equal to 3, right? So we replace the 3, replace the Z with 3. So get the areal integral. This guy is nothing but the area of the disk. And Z equals 0, so Z equals 0, this time just go away. So the volume is easy to calculate. The volume is just the radius is 1, so it's pi times 3. So pi is the area of the disk, and the 3 is the height. So it's 3 times 3 pi minus 3. We just said the area of the disk is pi, so it's just pi, which is 6 pi. Any question? Okay, I guess it's clear. So let's look at the problem 4. It's about calculate the volume and the surface. That's the area of the surface. Yeah. You can take a look and we can do this problem together later on.
Excuse me, actually, I want to ask the problem if we like revolve about the y-axis here instead of x-axis.
Actually, that is exactly the homework. Revolving around the y-axis is actually the homework. With exactly the same question, yes.
Yeah,
I feel like she must have made a mistake on the homework because if you try to revolve this around the y-axis, I think that's where all the confusion's happening. Like,
yeah, it's not bounded, it's not closed. That's the problem.
Yeah, exactly. So if it
upper one can be, down one can be.
Oh, okay. I haven't taken a look at the homework yet.
If it is on the y-axis, could you show us how to do this if it was revolved around the y-axis?
Sure, right. So
yeah, I just also get stuck on that homework question for a long time when we revolve about y-axis.
Yeah, the wording was just really weird.
Right. By the way, so whenever you feel confused by the wording, you should always ask the TA like during the exam, right? To avoid this kind of mistake. Right. So so for this one, okay. So if your okay, so this is x, y. So x. Okay, let's say this is x. This is y. This is z. Then this looks like this. Are you saying like kind of a revolve around the y-axis? Okay, so around the y-axis, then is something like it's kind of difficult to draw. Something like that, right? If you kind of flip this this shape, you get something like this, right? But it's kind of difficult to draw in this direction.
Yeah, like, can you tell me how to get from the picture about the integral range?
Oh, okay, sure. So let's.
Thank you.
Okay, sure. Let's look at the volume. Let's look at the volume. Okay, maybe it's kind of difficult to draw, but let's look at the volume. Okay, so basically, what we know that yeah, it's how to draw it. Oops. Basically, you look at the y, some random y, and okay. So if this is rotating around the y-axis, then here's 0. This point is the square root of 2, right? Because this is y equal to the x equal to this guy, so it's square root of 2. Meaning that the range of y is from 0 to square root of 2. For the volume, let's look at random y and also y plus dy. For that slide, let's look at the volume. The height, oops, the height is dy, right? Times the area, which is in this case is pi x squared, right? So the volume is given by, you know, the y is from 0 to square root of 2 is pi x squared. It's given by this. And we know the relation between x and y. So y equal to square root of x, meaning that this guy, meaning pi and y force dy. And then you can do this integral, right?
Can I introduce another problem? What about we have to find the moment and the density is not constant, so we have to use the triple integral.
You mean like so?
Yeah, moment, but like density is x,
Okay,
y, z.
so right, I see. So are you saying like I say, for example, okay, so let's create a problem by ourselves. Basically, we have a shape like this, and let's assume the density is the general expression like this. Let's find out what's the moment of inertia, right? That's I. What's this guy? So so to determine the integration region is also easy, because what we know is the y is from 0 to 0 to square root of 2, right? So from 0 to square root of 2, this is the first thing you determine the range of the y, integration of y. So once you have this integration region, you just choose a random y. Choose a random y, let's say here. Then random y, for fixed random y, corresponding to a disk, right? Because imagine y is a constant, and also combined with this kind of shape we just draw here, combined together is a disk. Meaning that the dz dx is integrating over a disk. The disk, by the way, to find the so this kind of a 9 is y equal to square root of x. What's the expression of this surface? First, you need to square this guy, and then square it. You get this one? And this is 4x squared plus d squared, I think. So basically for the integration region of z and x is given by x squared plus d squared smaller than y force.
May I ask how?
Okay, so
Because I use the cylindrical coordinate, which I don't have to deal with the z, so I could find the.
yeah, I mean, I'm dealing with the most general case, right? This
Yeah, but how did you add up the z square?
okay, so so here, because whenever you have a shape, you have a line, revolve like around some axis. First, you know the expression of this line, which is y equal to square root of x, right? So when you kind of revolve this line around some axis, so you always need to square it until this kind of, you can say in this shape, the x is equivalent to z. There's a symmetry in the xz plane. They are rotational invariant, right? In that case, I always need some square x square. Then once we have this expression, we can add the z square directly. This is always the expression of this area.
Okay, so you're saying you're using the symmetry property that if you change x to y, z to x, it should be preserved the same. That's
Right.
why you did that
Right.
calculation. Okay.
Yeah, you cannot say, okay, this definitely the surface of this guy is not given by this. You need to square to this kind of x square and then add a z square. This is a kind of a trick. When you do more and more problems, you finally realize this is true. Yeah, like what you said. This, by the way, now it's easy to write down the expression, right? It's just it's the what? The distance. The distance is x squared plus d squared. This is r squared, right? The distance from one place to the y-axis, and where's the rho x, rho y, rho z. So this is the general expression. Of course, like what you said, we can definitely use the like a cylindrical coordinate because this is a disk. This is a disk. For disk, we can always say x equal to y squared cosine. Okay, so let's say if we use the cylindrical coordinate, in this case, your r is, or rho, whatever like what variable you want to use, is from 0 to y squared, because the maximum radius in this case is y squared, and the direction, of course, is 2 pi theta, and then you can use the x equal to r times cosine theta, y equal to sin theta. Oh, here's not. Here's x. Here's z equal to sin r times sin theta, and plug in and use the familiar, a very common like cylindrical coordinate to solve this problem. Yeah, I mean the point is, let me add another page just to make it clear what's the punchline here. Basically, if I have a shape, let's say a general shape, a three-dimensional general shape, like this, x, y, z. Usually you can find one direction, like one, for example, in this case is z, is 0 to z naught. So first you need to, for the volume integral, or for you always need to fix the integration along the z first. then you need to integrate over the, whenever you fix it, meaning that you can look at a fixed z, and this guy will give you a two-dimensional integral, which is over dx dy. And you find out the expression for this disk, or in general, it's not a disk, it's a two-dimensional integral, something like, yeah, I'm not sure, you need to specify. And for example, let's say it's x squared plus, yeah, whatever. So just put it here. And the integrand is the integrand. For example, for the moment of inertia, it's just the distance to the axis, which is in this case is x squared plus y squared, and times the density stuff. Yeah, I guess the time goes fast, and time is up, and you're free to go if you have no question. If you have some question want to discuss, you can stay here, and yeah, we can discuss. By the way, I'll upload the solution later on, and so that you can look at those kind of problems. The solution.
Sorry, when you use the integral of the, like in problem 4 about the polar coordinate.
Let me stop recording first.